So welcome to another video. In previous videos we have seen how you can introduce vector norms and matrix norms. And as you may recall from your analysis courses, once you have norms, you can talk about distances. And if you have these things, you can talk about limits and also about sums, but not finite sums, but infinite sums, series. So in this video, we will be looking at a few more theoretical results. So something about limits and series of matrices, and also a little bit about how you can perturb a matrix. So if I go back to the slides here, then we have as an outline here that we will prove some theorems about limits and series of matrices. And then I will study how you can take a non-singular matrix, then perturb it. So perturbing just means that I change the entries in the matrix. And how much can I change them for the new matrix still to be non-singular? And I'll finish the video as usual with a couple of conclusions. So let's see. As I said, since we have matrix norms, we can add infinitely many matrices. And also we can form a sequence of matrices and study whether it has a limit or not. So the latter is what we will do now. So here is a theorem, and it tells us that if you take a square matrix A, and then if you compute power, so you're going to compute, it says here, a to the power k. So basically we will study a to the power 0, a to the power 1, a squared, a to the power 3, and so on. So this one is the identity, this one is just the matrix A, and you compute all these powers of the matrix, and what the theorem tells us is that this will converge to the all zero matrix. So big O is the matrix that has all zeros in it. That is if and only if, so that happens if the spectral radius of the matrix is less than 1. Now here, I always like to think that it is instructive to look at special cases. So for instance, if you would take a number, so if you would take a bit of a boring situation, but you take a number, so little r here, and r is some real number, so then I'm going to compute r squared, r to the power 3, and so on. Then basically what the theorem tells us is that r to the power k goes to 0 if and only if, well, the spectral radius of this matrix that is very boring, that is just going to be the absolute value of r. And this is something that you know from analysis. So if you have a number and you take powers, then if the number in absolute value is less than 1, then the powers will go to 0. So this is just a generalization to matrices. So the question is now, can we prove this? So let me grab a new sheet of paper here, and then we'll try and prove the theorem. So what I'm going to do is, it is an if and only if, so it's an equivalence, but I'm only going to prove, well, the interesting parts, say. So I will prove this, and the other one I'll leave. So what I'm going to assume is that a to the power k goes to the all zero matrix if I let k go to infinity. So what it means, and that is why we needed norms, is that the limit for k going to infinity, and then the norm of a to the power k minus the all zero matrix, so minus the limit of what it's going to be, should go to 0. And this should hold for a norm. So let's make a choice. So we are going to choose the 2 norm. So then we see that apparently the limit k is going to infinity, and then the 2 norm of a to the power k minus the all zero matrix, I don't have to write that, and the 2 norm goes to 0. Okay. Now, I need to tell something to prove something about the spectral radius, because this is what I would like to prove here, that the spectral radius is less than 1. So I need to have something about the eigenvalues. So let's pick an eigenvalue. And not just anyone, so let's make a new bullet here. Let's give myself a little bit more space. So let lambda be eigenvalue of the matrix A, of course, and such that the spectral radius equals absolute value of lambda. This is kind of the way that you can circumvent the situation that rho of A may not be an eigenvalue. So this is the proper way to introduce an eigenvalue, and the absolute value of that lambda equals the spectral radius. I also need an eigenvector. Let U be corresponding eigenvector. And as you know, if you have an eigenvector, if you multiply it with some number unequal to 0, you still have an eigenvector. So I can also scale it, and let's do that here. So let U be corresponding eigenvector with, let's give it in the 2 norm length 1. Okay, and I'm going to add a page here because I will need more space. So what we know is, because it's the eigenvector, we know that AU equals lambda U. Okay. Now, if I would apply the matrix A on both sides of the equation, let's do that here, then on the left we get A squared U. On the right we have lambda AU, but AU, that's lambda U, so this is the same as lambda squared U. And you will probably believe me that you can prove with induction, or you just say I see that immediately, is that I can generalize this to say that A to the power k U is the same as lambda to the power k U. That holds for every natural number k. Now I'm going to take norms. So now we have that A power k U 2 norm equals, and then I can pull out a lambda, so you would get absolute value of lambda to the power k times U 2 norm. And well, this here is 1, that's the choice we made for the eigenvector, and the absolute value of lambda, that is the same as the spectral radius, so rho A to the power k. Proof is almost done, because what we see here, so conclusion, we have that rho A to the power k equals norm A to the power k times U 2 norm. And with the properties that we have for induced matrix norms, we know that this is less or equal the 2 norm of A to the power k times U 2 norm. Again, this thing is 1, so that doesn't bother us. And we know that A to the power k, that was basically the assumption that we started with, that this norm will go to 0 for k tending to infinity. And this is just a number, so the conclusion is finally that apparently rho A is less than 1. So rho A is always a positive number, right? Or a non-negative number. And here we see that it has to be smaller than 1, which is what we wanted to prove. Okay, so that was the first bit. So I was talking here about limits of a sequence of matrices. Next, what I would like to consider is an infinite sum, so a series or an infinite sum of matrices. So I'm going to look at this here. So the sum k running from 0 to infinity, A to the power k. I'm going to say that this converges, that is equivalent to saying that the spectral radius is less than 1. So this is linked to the previous theorem, It is basically a consequence of the previous theorem. And there is a little bit more here. So also if it converges, so if this here is true and we know that this series converges, then the limit is identity minus A inverse. Again, if you look at numbers, then what this tells you here is that if you pick x in R with modulus x less than 1, then the sum is 1 plus x squared plus and so on, that this converges and is equal to 1 over 1 minus x. And you may recall from Taylor's series that this is indeed true. So this is a generalization of that result from analysis. So let's see if we can also prove this. And the proof is quite elegant. So let's see the proof. I'm going to need a bit more space for that. So what we need to consider is that sum that we have here. And very often if we want to prove that such a series converges, we first look at the finite sum and then we take the limit of the finite sum. So that's what I'm going to do here too. So I'm going to introduce Sn be the finite sum. So that's going to be the sum. K is running from 0 up to capital N, a to the power k. So if you would write that out in terms, what you get is that Sn is a to the power 0, that's the identity matrix, a to the power 1, a squared, and so on. And then here we have a to the power n. That's the very last term in this finite sum. Now I'm going to multiply everything with a. So I'm going to say a times Sn. Well, if I do the identity times a, I get a. I write it here. If I do a times a, I get a squared. A squared times a would be a to the power 3. I'm not going to write that down. And here we have a to the power n, and there's going to be one more term, a to the power n plus 1. Now, if you subtract these, you see that most of them will drop out. So what we get is that identity minus a times Sn, that's the left-hand side. On the right-hand side, almost all of these terms drop out. Only the identity we have from the first line that keeps in, and from the last line we have a to the power n plus 1. And then basically we're done, because what I want to do now is I want to let n, capital N, go to infinity. Then this thing will be the series that we're looking for. This thing with the theorem that we just proved about limits of matrices or sequences, this will go to 0, and then we're basically done. So how can we do that a bit more properly? So we assume that rho A is less than 1. And then with the previous theorem, we know that a to the power n plus 1 will go to the all 0 matrix for n going to infinity. And I'm going to consider this thing here, because I would like to free Sn, if you want. So I would like to multiply with the inverse of this matrix, but first I have to show that this inverse exists. Now, that is not too difficult, because if lambda is an eigenvalue of A, so say AU equals lambda u unequal to 0, then identity minus AU is the same as u minus AU is u minus lambda u is 1 minus lambda u. So what we see here is if you take an eigenpair, eigenvector, eigenvalue of the A matrix, it gives you an eigenpair of identity minus A. The new eigenvalue is going to be 1 minus lambda, and the eigenvector is the same. Now, if we know that all the eigenvalues are less than 1 in absolute value, then identity minus lambda can never be 0. So because rho A is less than 1, 1 minus lambda can never be 0. So what we find, in fact, is that 0 is not an eigenvalue of identity minus A, or identity minus A is non-singular. So what we see is that it's non-singular. That means that the inverse exists, and that means that I can write Sn as identity minus A inverse times identity minus A to the power n plus 1. That is what we found from the previous slide. And this will converge to identity minus A inverse for n going to infinity. And that is what we wanted to prove. So that completes the proof. Now there is one more theorem that I would like to prove. As you see, there are many proofs this time. And that is called the perturbation theorem. So let's see, what do we have here? We have a non-singular matrix A. So non-singular, it means that A inverse exists. And now what I would like to do is I would like to look at A plus B. So you can think of B as a perturbation. I'm going to change the entries in my A matrix with the entries of B. So every single entry of my A matrix I can change. I have some norm. And now what this theorem tells us, if B A inverse, so A inverse exists, if the norm of this thing is less than 1, then A plus B is still non-singular. So even though I changed my original matrix A, the new A plus B is still non-singular. And also I have some sort of error bounds, you might say. So A plus B inverse, the norm of that thing, is related to the norm of A inverse, and we have these inequalities here. So let's see how we can prove that. And that proof is the last bit of this video. So what I am going to do here is I have A, which is non-singular, and I have A plus B. From this B matrix, I know nothing. I assume nothing. I do not assume that it's that it has an inverse, and I would like to show that A plus B is non-singular under the condition. So I'm going to assume that B A inverse is less than 1. Now that may seem like a bit of a strange assumption, but it will become clear in a second why we make this assumption here. So what I'm going to do first is say, well, the spectral radius of BA inverse, so that's the biggest absolute value of the eigenvalues. We have seen that the spectral radius of any matrix is less or equal any induced matrix norm. And this one we have assumed to be less than 1. So we see that the spectral radius of BA inverse is less than 1. And with the theorem that we have just shown about the series, we now know, well, we have seen that in the previous proof, I mean. So we know that identity plus BA inverse is non-singular. Because identity plus BA inverse has eigenvalues 1 plus lambda. All the eigenvalues are less than 1 in absolute value. So identity plus BA inverse is going to be non-singular. Now, where does this all come from? Well, if you take identity plus BA inverse and you multiply from the right with A, you get A plus BA inverse A, which is A plus B. And we wanted to say something about A plus B. So the conclusion is, this thing is non-singular. This thing is non-singular. So then we know that this thing is non-singular. So that bit was easy. Now, to get to the other estimates, I'm going to use the following idea. So this was the first bit. And next, what I'm going to do is I am going to say that so the basic idea is we have A is non-singular. B is small in some sense. In what sense? Well, in this sense here. So let's say B is small. So I put it between quotes because it's a bit of a hand-waving argument, and I'm going to do it mathematically, so it's going to be strict. But the idea is that A plus B is still non-singular. And hopefully A plus B inverse looks like, again quotes because it's a bit of a hand-waving argument, looks like A inverse. So let's do this a bit more mathematical. So if I say that A plus B inverse looks like A inverse, well, what it means is that A plus B inverse is A inverse plus C, and hopefully my C matrix is also small in some sense. Yeah? So let me grab some more writing space. So I am saying that A plus B inverse equals A inverse plus C. Okay. So now I'm going to play around a little bit with all the definitions. So we know, if you multiply A plus B with A plus B inverse, you get the identity matrix. Now I'm going to plug in basically my definition for C. So this is the same as A inverse plus C equals the identity matrix. And next, what I am going to do is rewrite this a little bit. So what I do is I multiply everything out. So this thing times this thing and this thing times this thing. So what we get is A times A inverse, that's the identity, plus AC plus BA inverse plus BC equals the identity. I can subtract the identity from the left and from the right of the equation. AC plus BC is the same as A plus BC equals, and I move the BA inverse to the right, and then it gets a minus sign. So apparently I have found a new expression for my C. C is the same as minus A plus B inverse times BA inverse. So the conclusion that we have, we started here with this definition for C. Now I've also found this here. So if I put that together, what we get is so A plus B inverse is A inverse plus C is A inverse minus A plus B inverse BA inverse. And as you see, this directly leads to the inequality that we wanted to prove. One of the two, there are two inequalities in the theorem. So now if you take matrix norms, then you see that the norm of A plus B inverse, and I'm directly going to be using the triangle inequality, so I'm going to say that's less or equal, and then here we have the norm of A inverse plus, and then here we get A plus B inverse norm times, I'm making it bigger, BA inverse, like this. So if you move this term to the left side of the inequality, and then you divide by the 1 that's in front of this, minus the norm of BA inverse, then you get the first inequality in the theorem, and you can prove the other inequality in the same way. So that concludes what I wanted to prove about the perturbation theorem. So let's wrap up what we have seen in this video. So we have seen that if you have matrix norms, you can use that to consider sequences and limits of sequences of matrices, and also infinite sums or series of matrices. And we have also seen that when you take a non-singular matrix, basically how much you can perturb it and still have a matrix that is non-singular. So quite a few proofs in this video. In general, there will be fewer proofs. I also did not do complete proofs. So I like to give proofs when they give some additional insight. And this one was a bit proof heavy, so hopefully less proofs in the next video. And I'll hope to see you there. Thank you.